Hello, thanks for spending some time with me today. I want to start this talk out by saying that I am truly honored to receive the award that's associated with this talk. It's been a long career, and I've worked very hard across that period of time. But the truth of the matter is that I've always taken an approach of ruthlessly working on whatever it is I thought was interesting or cool or especially fun at any given time. And that's where the fun in the title here is coming from. And so it's particularly gratifying to find out that, in fact, other people appreciate the results that I've been able to get when I was feeling like I was doing this to have fun. All right. Now, winning an award like this inevitably tends to make you think a little bit about the past, and I certainly did that. But I'm not very interested in the past. I find the future much more interesting. And so I'm not going to do a retrospective of my work here, if that's what you came for, sorry. Instead, I really want to talk about the future of interactive technology. Okay, now, this is not the future of all of HCI. I'm interested in the technology part of that. It's not the only part of HCI work that I do, but it's always been sort of my interest and my concentration. And so that's what this talk is going to be about. Now, my first thought about the future of interactive technology is really that, well, the future of interactive technology has changed some over the years of my career, right? Some of our past futures have, in fact, arrived. So video teleconferencing, boy, has that arrived. We are all doing that today, right now. My smartwatch, that has arrived that you see here. And in fact, if I was able to take this watch back to 1981, where this cover was done as a joke, this would be the fastest computer on the planet. And we see this cute little robot scampering around the floor here. That looks a lot like a Roomba, and that happened. Okay, so some of our past futures have arrived. But a lot of our past futures, well, not so much. We are not flying around in flying cars. We do not have the jetpacks that we all would really like to be flying around in. We don't live under transparent domes. We don't ride around on monorails. I don't know what this kid was supposed to be doing, but whatever it is, we're not doing that, okay? And so really a lot of our past futures didn't show up. And this means, not too surprisingly, that we're not really particularly great at predicting the future. But I think it's still important to think about the future, even if we shouldn't have an expectation that we can predict it very well. Right? And so today what I'm going to do is to take a little slice out of this very big and hard topic of the future and the future of interactive technology. And in the end, all I really want to do is suggest that you should be thinking a little differently about the future now than we have thought about the future in the past, and that there are some systematic reasons for why we should do that. Okay? I won't try to be comprehensive. I'm not going to try to predict much very specifically. I'm really just going to focus on a few exemplars that I think illustrate the kinds of points that I think we should think about differently thinking into the future now than we had thinking into the future in the past. So I'm going to talk about some new approaches to old problems as one way to do this. I'm going to talk about some old approaches to new problems. And somewhere along in here, I may not do anything new at all, but maybe I will. Okay. But before we do that, I think we need to talk about what is the elephant in the room for almost any discussion of future technology. If we look at it, probably the biggest agent of change has really changed remarkably little over time. And that giant agent of change has been the exponential growth of computing that has been predicted and predicted very well by Moore's law. Okay, and so here we have sort of a schematic chart that represents this huge growth in computing power that is predicted by Moore's law. Now, I can hear part of the audience here saying, well, wait, hold on. Clock speeds stopped doubling years back. Isn't Moore's law dead? Okay, well, the short answer is, well, actually, no. Moore's law is not dead. So this chart here shows Moore's law over a remarkably long period of time. And if you look at the right-hand side here, it ends in 2020. So this is relatively recent data. And remember, this is a log scale on the y-axis here. So this is exponential growth. And no, it hasn't stopped, all right? Now, that said, we do need to recognize that it is going to be harder to make use of computing power in the future than it has been in the past. In the past, we had clock speed doublings, and that's not happening anymore. That meant that we could take exactly the same, essentially exactly the same code, and it ran twice as fast 2 years from now than it does now, right? And that isn't happening anymore. We're getting doubling of transistors, but it's not going into doubling of clock speeds. It's going into number of processors that we can use simultaneously. And in fact, we can see that in this chart. If you are able to get in really close to this, you would be able to see that the top 7 points on this chart are actually GPUs. Okay, and those are architected quite differently, and it requires that you program them quite differently in order to get the computational power out of them. So it's harder to make use of the increase in power than it was before, and that is definitely true. But even if you take GPUs out of the picture, then, and so this is a different chart that's just looking at conventional CPUs here, and now is running in transistors from 1,000 to 50 billion on a log scale, and it runs right up to current times, definitely still happening. But we do, again, need to recognize that this can't go on absolutely indefinitely. Eventually, it has to plateau, although the predictions that it would plateau have been around for a long time. Sometime between here and there, it's going to start to slow down is what's going to happen. So the doubling times are going to extend, and they're going to be less predictable. But we are still talking about having doubling times and an exponential growth. So it's still happening. So my response to all of this and this objection is, Moore's law is dead, but long live Moore's law, at least for quite a bit of time in front of us. All right, so let's go back where I was in the talk. I think any talk about the future really needs to consider this exponential growth predicted by Moore's law. Now, I know you're thinking, really? You're going to tell me about this? This is the oldest news on the planet. I have known about this since I was 12. It is fully incorporated into my thinking about my future research. I'm here today to convince you that no, actually you don't understand Moore's law, that it really does matter, and that what you should be thinking about should incorporate much more thinking about Moore's law than it has in the past. Okay? And why is that? Why is it that we don't understand Moore's law despite the fact that it's been around for a very long time? Well, the reason is that it's very hard for human beings to understand exponential growth. So I have this little schematic chart here that represents exponential growth. On the y-axis, we have good stuff resulting from transistors, nice labeling, and then I have time in this direction on the x-axis, which I've conveniently left off the units of. But schematically, the important thing here is that this is a really steep curve. It increases very rapidly. That's what exponential growth is about. Okay? But as I say, it's very hard for human beings to understand exponential growth. So I'm going to do 2 thought experiments today to try to help you understand Moore's law and the exponential growth with it more fully. So thought experiment 1 starts by saying, and sort of I think we all recognize that there have been absolutely monumentally huge gains in computational power since the old days. I will just pick 1965. So this is maybe what computing looked like in 1965. Okay, computers were very big things sequestered away in rooms and so forth. We can compare that with the computing power that we have today. We can compare both of just the magnitude of the power, but also the impact that it has. Okay, and so think about for a second, try to hold it in your head for just a second. The huge size of that change. It's really, really big amount of change. Hold it in your head for a second. Now, what does it mean to double every 2 years? And that's what Moore's law predicts. Well, that means that all of that change that I'm asking you to hold in your head, that magnitude of change, all of that, every single bit of that happens again. And it happens again in the next 2 years, not the next 40 years or the next 60 years, but it happens again in the next 2 years, every single bit of that change. That's a lot. Okay? And again, it's not happening over the 60 years that it did in the past. It's happening in 2 years. It's happening between when sophomore CS students right now, between now and when they graduate. It is happening before if you're an academic like me, it's happening before the end of your next NSF grant, or if you're really an academic like me, before your next NSF grant gets funded. Okay, all of it, absolutely every bit of it is happening again in 2 years. That is big. Now, let's go to thought experiment number 2. Now, this is a thought experiment that I heard in a talk by Douglas Engelbart quite a few years ago, and it starts like this. Suppose you and everything you can see suddenly gets exactly 10 times bigger. So you're in some sort of a closed room, you and everything you can see gets bigger. Could you tell the difference? Do you perceive a change? All right, think about that for a second. I think the kind of most common answer, and maybe the common sense answer, is no, I don't perceive a change. I can't tell the difference. And that's going to turn out to be the right answer, but not for the reason that you think. Okay, well, let's do a little bit of analysis here. Well, first off, mass scales by volume. Okay, so you just got 1,000 times heavier. But the strength of your chair depends on sort of the post in the middle of the chair there, and that scales, the strength of that scales by the cross-sectional area of that. And that's got 100 times stronger, but relatively speaking, you just got 10 times heavier, and your chair is not designed to handle that. And so your chair collapses under the weight of that 10-fold change in the ratio. Okay, and you might notice that, you might, okay. But in fact, that will not seem so important to you because most of your bones will break for exactly the same reason, at least by the time you hit the floor, and you'll definitely notice that. Okay, except maybe you won't notice that because it turns out that oxygen consumption of your cells scales by volume, but the cell's ability to absorb that oxygen scales by area. You just instantly lost 90% of your oxygen. You will be unconscious before you hit the floor and dead shortly thereafter. So no, you won't notice the change at all, but not for the reason that you thought. Right? Now, the moral of this story is that large changes have a huge impact, and this was 1 order of magnitude of change. And this is particularly true when you have differential scaling rates. Okay, and I want to point out that this is us now. Okay, we are expecting multiple orders of change in computational power happening over a relatively small number of years, not just 1 order of magnitude, but multiple orders of magnitude. And we definitely have differential scaling. Okay, we have sort of the potential provided by computing power down at the bottom, if you will, and we're trying, at least in HCI, to use that power to change and to make things better for people, but people's abilities are, by that scale, really not changing at all. So we definitely have differential scaling. So these 2 thought experiments together should tell us that the amount of impact that we could expect to see from this technological change is incredibly large, and it's even much, much larger than the impact that we have seen in the past, despite the fact that that seems very large. Okay, now, by the way, how much computing power do we have right now? Well, this might surprise some of you. So right now you can buy about a $1,500 graphics card, not cheap, but you can just stick it in your PC that has NVIDIA Ampere architecture chip on it. That has about 45 billion transistors. Right? You can tell that's a big number, but it's a little hard to tell what that really means. So let's talk about speed, for instance, or total computing power. So the peak speed, now you're not going to get this peak speed because you can't get every single part of this device to deliver all of this computation at once. But if you could squeeze every bit of computation out of this device, it's going to clock out at 330 trillion floating point operations per second. Right? And we can recognize that's large, but it's hard to understand trillions. So let me relate this to something else. This means that you have 3,300 floating point operations every second for every single neuron in your brain. Okay? And you may also be thinking, gee, can I simulate a neuron with 3,300 floating point operations per second? The answer may be yes, but that's a different talk. Another way to look at this is we have over 10,000 cores. Now, these aren't all independent. A lot of them have to be executing the same instruction at the same time. But in comparison, let's compare this to the first microcomputer. Okay, the first microcomputer really changed things. We often think of it as sort of starting the revolution, or one of the revolutions that lead to the big change here. But for every single transistor in that microcomputer, there were 2,300 of them, we have about 5 full computing cores in this device. So in the end, we have a lot of computing power right now. Now, it may seem that that puts us up at the top of this curve. We've seen a huge amount of change, but the interesting thing here is that the really interesting implications of Moore's law, the big changes, are all in front of us because of the exponential nature of this change. We are not at the top of this curve. We are at near the bottom of this curve. And statistically speaking, almost all of the change is ahead of us, not behind us. And for me, that makes me very optimistic about the future. Lots of fun stuff is ahead of us. And that's why I think all of the fun is ahead of us. Now, what should we do with this? Okay, well, unfortunately, I only have 15 minutes here. This was really just a teaser for a second part of a longer part of the talk. But I won't leave you completely hanging. As a preview of that, one of my conclusions there is that some of our intuitions, and these are intuitions that have been developed over quite a few doublings if you think about it, are leading us astray. And to fight those, we need to take on a mindset of finding ways to almost just waste cycles in service of the user, to use what in the past would have been essentially impossible, but we certainly would have never thought of using that many cycles to serve the user interface and to serve the user. But that's how we need to think about things if we're going to make proper use of what's ahead of us. All right, there is this longer talk. I hope to see you there. You can find this continuation near where you found this recording, either on YouTube or the ACM Digital Library, but there's also a link that you can find on this page. So if you type bit.ly/Scotts_talk into your browser, that will take you to a page that will provide you with a link to that second recording. And I hope to see you on the other side.